So we're moving on to chapter 3, I think it is, which is the first chapter involving graphs. There are a few things I still want to do from chapter 2. I'm going to loop back to them later. Right now I want to move on to this. So we're going to talk about graphs. So there's a formal definition of a graph: a set of vertices and a set of edges, where an edge is a pair of vertices. So this one has 7 vertices and whatever, how many edges that is. And the thing about graphs, the way they differ, you think graphs are similar to, say, binary trees. They're used very differently in programming. Binary trees are typically used to make some algorithm more efficient, whereas graphs are used to represent some aspect of the real world. So what are some aspects of the real world you could use a graph to represent? Yeah?
Airports.
Airports meaning like flights between airports, okay?
Distances between routers.
Distances between routers and a computer network, sure. Yeah?
Traffic flow.
Traffic flow on roads. Okay? Yeah?
Relationships on Facebook.
Okay, relationships on Facebook. That's a graph. All the web pages in the world form a large graph. If you view the edges as being this web page links to this web page, there's an edge. And so Google is basically working on an enormous graph. Mapping software is working on a map of the roads. When you try to schedule a trip on a travel website, an airplane trip, it's finding, the flights are graphs. It's got to get you from here to there, and there are lots of choices, and there's fares to consider and all that. So there are lots of uses for graphs. And so there's efficient graph algorithms are really important and used all the time. We're going to you're used to using n when we need to characterize the size of something. But when we work with graphs, we've got 2 things we've got to worry about: v and e. So v is the set of vertices, and e is the set of edges. Now, sometimes I will say v when I mean the set of all vertices, and sometimes I'll use v when I mean the size of that set. And the same thing with e. Sometimes it's the set of all edges, sometimes it's the size of that set. It's always clear from context which I mean, whether I'm talking about a size or I'm talking about the actual edges. So this particular graph here, those are the vertices. That's the set V, and that's the set E. That's the rest of the set E. And I also will say V is 7 or E is 9, because that's the size. Now, why is this true? Why is E, regardless of the graph, why is E always O of V squared? Yep.
The maximum number of connections between each vertex and every other vertex would be V squared.
Okay, so pick any vertex, like 1. You can have 7 edges out of this vertex 1. You can have an edge to yourself. Usually don't see them in an undirected graph, but you do in directed graphs. Then an edge 2, 3, 4, 5, 6, and 7. So each vertex can have 7 edges out. And there are 7 vertices, so that's the most edges you can have, 7 squared. Now you could have none. So you got anywhere between no edges to V squared edges. Okay? So here's a picture of a use of a graph. What are we doing here? How do we reduce this map of Australia to a graph? Yep.
Position them by their positions, and then by what they're connecting to. Okay.
So essentially, somewhere else there's got to be information that says Western Australia is represented by vertex 1, and Northern Territory by vertex 2. But this just shows for any two states or territories, do they border each other? Got a question?
I was going to give an answer.
Okay.
Yeah, the vertexes represent territories and the edges represent borders.
Right. So let's see, Tasmania is 6, so it borders nothing. Victoria borders 2 things, and so forth. So you can tell this graph abstracts the border information from that. Okay, here's an rather old visualization. It's probably 5 or 10 years old now, of the World Wide Web. And so it's a picture of websites, web pages, and edges between them, links between them. And this previous graph, I don't think I mentioned it when I was there, it's an undirected graph because there's no directionality on the edges. If one state borders another, then vice versa. But here, the edges are directed. So this is an example of a directed graph. One web page can reference another, have a link to another, but not vice versa. So what do you see when you have, what artifacts do you see when you look at that graph of the web? What are the bright spots? Yeah?
I could guess like Facebook, MySpace, Twitter, all the big websites. Right,
I mean, I'm just guessing too, but a bright spot would be lots of pages that are all interconnected. So lots of space, a large number of edges compared to the number of pages. So that's sort of a clump where everything's self-referential. And then out here on the border, you see isolated ones. So there'll be web pages that no one links to, for example. Or it's possible, I guess, to have web pages that don't link to anything else. So kind of have to let your imagination run to use that to visualize the web. But that's a directed graph. Okay, here's another kind. This is also a directed graph, but it's acyclic. There are no cycles. Can't go around in circles. And so this is, for example, a piece of the prerequisite graph for computer science courses. So I think one is maybe 1400, 2 is 1410, 3 is 2420. And it just says you've got to take course 1 before you take course 2. You've got to take course 2 before you take course 3. You've got to take both 4 and 3 before you take 7. So that's a directed acyclic graph which handles this situation. All right? This is called a weighted graph because now there's information on the edges. So in this case, the vertices represent cities in Texas, and the edges represent the highway miles on major roads between those cities. And so if you want to plan a trip from 1 to 7, you need to find presumably the shortest path between them. So that's a directed, an undirected and weighted graph. Okay? Now this is a weighted directed graph. And I have to apologize that the arrowheads aren't showing up here. But the idea is that these are one-way edges. I'm not sure where the arrowheads went, but anyway, maybe it takes 65 minutes to get from 1 to 2. So there's an arrowhead. And 45 minutes to get from 2 to 1. Why would that be different? This is a sort of an abstraction of a hiking map. Yeah.
There could be like traffic going uphill and downhill.
Well, yeah, it's not as much traffic, it's just hills, right? Yeah. It's just, we're walking, so it's just slower walk uphill. And then maybe there's a network of one-way trails. I don't know if I've ever seen, maybe I've seen a one-way walking trail before. I've certainly seen one-way biking trails. So imagine this forms a cycle here. So you can have weights on a directed graph. Now, so it's not hard to imagine ways to use graphs. And it's not hard, but we got to talk about, though, how to take graphs. Once you've abstracted from some real-world thing and rendered it as a graph, how do we represent it in a computer? And there's 2 common approaches. The first one, the simplest one, is called an adjacency matrix. It's essentially a V by V array that stores information about every vertex, about every edge, rather. So for example, on this one, so this is that same graph we saw before, but this time with arrowheads. We have an edge from 1 to 2 that's weighted with 45. And so here, this is the from 1. Imagine this is index starting at 1. So from 1 2, 2 is 45. From 2 to 4 is 20. 2 to 4 is 20. So we store the weights and the rest some null value or 0 or something, whatever is appropriate. So that's one option, adjacency matrix. Now, if the graph isn't weighted, then you can still use an adjacency matrix. It just becomes ones and zeros, trues and falses. So it becomes more compact because you've got a bit array now, not an integer array. Now the problem with the adjacency matrix is it takes a lot of space. It takes on the order of v squared space. Because you've got to store, well, because of the size of the matrix. So that space becomes prohibitive pretty fast. What would it look like if we stored, what would an adjacency matrix be like if we stored the bordering information for states in the US? How big would that array be? Be 50 by 50. Not so bad. Now, what if we stored the connectivity information of the World Wide Web in a adjacency matrix?
Oh dear, my heat.
There would be an entry, however many web pages there are in the world, there would be that many rows and that many columns. And I think someone calculated, the result still may be true, that there's not enough memory in the world, not enough computer memory in the world to store that adjacency matrix. So sometimes this works, sometimes it doesn't. Okay, so when I say v squared space, it could be v squared bits, it could be v squared integers. Just depends what the value is. The other option is an adjacency list, the other common option. And here, we just have an array of length v. So you can think of an entry in the array for each vertex, 1, 2, 3, 4. And then we have a list of edges out. So this is the edge out of vertex 1. These are the two edges out of vertex 2, and so on. So how much space does that consume? And we analyze algorithms, we're going to have to get used to counting in terms of both v and e. Yeah?
It would be order of v plus e.
V plus e, order of v plus e. It takes space proportional to v for the spine up there. And it takes space proportional to e for all these edges to be stored. So v plus e. Okay? So that was that must have been that's a directed graph, and I'm not sure what my point is here. Oh, this is what happens when you take out the weights. Right? If the edges don't have weights, you don't have to, obviously you don't have to store them, the representation gets a little smaller. That is a undirected graph. And so each edge gets stored twice. Because this edge both comes out of one and comes out of two. So it's stored in both places. But still e plus v. E plus v. And there's the same thing without actually storing the weights. Okay. So we have to ask ourselves which is better, which you would use in practice. So here's some observations. First, some definitions. A sparse graph, we're going to call a graph sparse if it has O of v edges. So if the number of edges is proportional to the number of vertices, we'll call it sparse. And we're going to call a graph dense if it has omega of v squared edges. So if there's, there's a quadratic relationship between the number of vertices and the number of edges. So let me start by asking this question. What's more common in nature, in reality? Sparse graphs or dense graphs? When you're modeling things from the real world. Yeah, I heard of dense, I heard of sparse. Well, let's start with the World Wide Web. Is that a dense graph or a sparse graph? Extremely sparse. What would it mean for it to be dense? Yeah? Yeah, to be dense, essentially, roughly every page would have to have a link to every other page. And we certainly don't see that. Every page just has a few links out. Typical page just has a few links out. So it's very sparse. And so it still take a lot of memory to represent it as a graph, but it is a sparse graph. What about a map of the interstate highway system, where the vertices are cities or intersections of interstates, and the edges are the segments between the intersections? Is that sparse or dense? Okay, we don't have general agreement here.
More dense. Most cities have multiple ways to take.
Okay, let's take Salt Lake City. So I-80 and I-15 cross. Okay, so there's an edge that would go from Salt Lake City to Ogden, where I-84 comes into I-15. And there'd be an edge, so I'm ignoring 215 at this point. There'd be an edge from Salt Lake City to I-80 going west. Where do you get an interstate? California somewhere. I-15 going south, you go all the way to where what's the one at the bottom? I-70 comes in. Okay? So there are lots of intersections of interstates, but there's only a few edges, a few edges out of each vertex. So it's sparse again. What about you made a graph of the wiring diagram of your house? So basically the outlets and the switches and the circuit breakers were the vertices and the wires are the edges. Is every outlet wired directly to every other outlet? No, hope not. That'd be very expensive. It's sparse. Typically, it's actually a tree, I guess. Okay? Yeah.
The internet has more links than websites. Is it sparse?
No, just because there's more links in websites doesn't mean it's sparse or not sparse.
Okay, because O of V
Right.
should be the website.
O of V doesn't mean at most V edges. You could have 100 vertices, 100 edges per vertex. It's still sparse. As long as that's a constant, it's still O of V. Okay? So what is a sparse graph? A dense graph. Can you think of an example of a dense graph? Yeah?
Gravitational effects.
Okay, so if you wanted to have a graph where the vertices were particles of matter and the edges were gravitational attraction between each pair, that would definitely be a dense graph. But it's actually hard to think up examples of dense graphs. Most graphs are sparse.
With one where a sports team has to travel to every other city in the league, so you represent it like that. So with each, like,
sure,
yeah, like the Jazz have to travel to every other.
All right, so if your graph was, say, teams in NBA and their edges, there's an edge out if a team has to travel to play a team in another city, that'd be a dense graph. Okay, so the rule of thumb is, if we have a sparse graph and we use an adjacency matrix to represent it, how much space does that take? V squared. I mean, it's completely insensitive to how many edges. So you take a sparse graph, you take a graph with no edges at all, it's still going to take V squared space to store it. Now, in terms of V, if you have a sparse graph, how much space does it take to store the JC matrix? Just in terms of V. We know this is O plus E, but how can we eliminate the E from the comparison? Okay. Yeah?
You have no edges?
Well, let's not make that assumption. Let's just assume that the graph is sparse. How can we simplify the space required for it? Yeah?
It's sparse, we know it's on the order of the edges.
Right. We know that E is O of V.
And then we know that V plus C is still O of V.
Right. So O of E plus V, and we know E is O of V, we can just replace E with V. We get O of 2V, which is O of V. So for sparse graphs, definitely you want to use adjacency list. And what about a dense graph? Suppose you have V squared edges. Okay, that's still going to take V squared. How much space is this going to take?
V squared.
Well, that part will take V, right? But then you got V squared of these guys. So V squared plus V is V squared. So it seems like a wash. maybe we should always use adjacency list and never use a matrix, because even in the worst case with their v squared edges, they both take space proportional to v squared. What do you think?
The matrix affords faster access.
The matrix is, there's quicker random access to this, there's not random access to this. Okay, what about just space, a space argument? Which would be superior if you got v squared edges? Yeah?
In a matrix, you're only storing every edge once, and the list might be a lot more redundant.
Well, you could argue you're storing every edge twice up here as well, because if it's undirected. Yeah?
Do we care about in terms of resizing the list?
No, typically we don't worry about that. Are all v squares similar, are the same? Yeah?
Each link has the point to the next.
Yeah, there's a lot more space overhead here. Up there, I'm just storing v squared, in this case, bits. Down here, I'm storing v squared integers and pointers. So this constant's much higher down here. This would take a lot more space and be slower to access anyway. So that's why I say that if we are doing a dense graph, we use a matrix. A sparse graph, we use a adjacency list. That means that when we analyze algorithms, we have to ask ourselves what representation are we using. So a lot of times we'll have to do two analyses. One, assuming we've got a dense graph. One, assuming we got a sparse graph. And sometimes the details of algorithms change, depending on what representation you're using. Okay, so let's talk about some simple operations. Is there an edge from U to V? If you ask that question on a matrix, it's constant time. Why?
Just a 2D array.
Yeah, it's just a double index. You index row U, column V. On a list, it's a little harder to say. It's O of V, certainly. Why can you say it's O of V? Or in fact, what's the limiting thing? What can make it slow to find out if there's an edge out? You got to traverse the list. See if it's there. So to find out if there's an edge out, it's governed by the length of that. So that list cannot be longer than V. Why not? Right, because you can't have an edge, more edges than one to every vertex. Why is it also O of E? What's the length of the longest list going to be O of E? Yeah?
Because if you store all edges in one area, then you'll still have just E traversals.
Right. You can't have more edges than there are, this can't be longer than the total number of edges in the graph. So basically, we sort of got to say that. It's O of E, it's O of V. It's O of the min of the two, if you like that. What about asking, is there an edge out of U? So we're not asking, is there an edge in a particular place? Is there an edge out? This is more expensive on a matrix. Why does it take O of V time to find out if there's an edge out of U? Yeah?
So it's because we only care if there's a list out of,
Yeah, but what's the worst case up here to find out if there's an edge out of a vertex? Maybe it's all zeros all the way across, and you've got to check all the way across to find out there's no edge. On the other hand, on a list, it's always constant time, because you just go and you see. If there's a null stored here, you know there's no list. If there's a not null stored there, you know there's some edge down here, so you can answer in constant time. Okay? And edges out of U, similar, I won't belabor that. It's similar to the other question. Now, here's our first algorithm on graphs. And we're going to work with undirected graphs. It's called Explore. And the way Explore works, it's given a graph and a vertex. And the job is to systematically visit every vertex that's reachable from that initial vertex. So if we explore starting at B, what vertices are we going to visit in the process? A, B, C, D, and E. If we start exploring at G, we should visit G and F. So there's sort of two chunks here. And we're going to assume we have an array visited that's indexed by vertex. And initially, every entry is false. And that tells us whether we're going to use that in the algorithm to determine if we visited it or not. So initially, we haven't visited anything. So let's see how that works. So we're at A right now. So we've called explore starting at A. And see what we do is, first thing, we mark the thing as visited, and I've indicated that by just turning that thing yellow. So we marked it as visited. Then we call this previsit method, which for now does nothing. We'll eventually do something with previsit. Then for every edge out of V, so from every edge of this form that starts at V and goes to U, if you haven't visited, we call explore recursively on it. Then when we finish dealing with every edge out of V, we post-visit V. So it's important to understand the order in which the lights turn on. So now that we visited A, what do we do next? Which two vertices are we going to visit next in that loop? B and D. And we have to make an arbitrary choice. It's just a coin flip which to go to first. And just so that I had to make the choice somehow, I always made it alphabetically. So we got B and D. We'll just do them in alphabetical order. So we go visit B. Okay? So now we made a recursive call to explore. What's B going to do? It'll go visit C. What's C going to do? It's going to consider, it has to look at this edge back to B. Why is it not going to follow it? Because it's already been visited. And so C has no unvisited vertices next to it. So we go back, we return from the recursive call to C. B's loop picks up again and we try the other edge out of B, which gets us to E. E's going to try to go to B. That won't work. It's going to go to D. What's D going to do? It'll consider going to A, but it's been visited. It's going to consider going to E, but it's been visited. So the call to D returns. Well, I don't think I have that animated. The call to D returns, and then C returns, B returns, A returns. And then we finally get to that top method call. It's going to try visiting D, but that's already visited. So we get a recursive call for each vertex. Now we're all done. The edges that we actually followed are colored yellow, and they're called tree edges. And the white edge there is called back edge. We didn't use it. It's an edge, but we didn't use it. So that's what explore does. And explore is fundamental to the next few algorithms we're going to look at. Yeah?
What does previsit and postvisit do?
Previsit and postvisit do nothing at the moment. What we will do is have them do stuff, and then we'll have a different algorithm. Okay? So that is explore. Very important to understand explore. Yeah?
For the back edge, how come we didn't use A to D? I thought if you would go back up to A would try to go to D?
It would try to go to D, but it will find out that D,
Okay, so,
it'll hit this and skip the call.
yeah, okay,
So I color it yellow when we actually made it, when we
okay.
did the explore. Any other questions? All right, now we're going to use explore to create an algorithm called depth first search. And depth first search is similar to explore, except we don't, with explore, we started at A, and then when we visited everything we could, we stopped. Depth first search wants to visit every vertex. So when it gets stuck, it will go find an unvisited vertex and restart the search. So it'll visit all the chunks. So let's see how it works. It first marks every vertex visited, unvisited. So it sets every visited to false, which we're modeling with just having all the vertices be white. And then for each vertex, if it's not been visited, it explores it. So let's think about from depth first search. It's going to loop through the vertices, so let's loop through in alphabetical order. What's going to happen when it considers V to be A? So it finds A right here. It finds out it's not visited. It's going to call explore. What happens when explore gets called? Yeah?
It's going to repeat the exact same pattern that we just did.
It's going to do what we just saw. It'll color all these vertices here and return. Then what will depth first search do? The loop will continue. Next up is B. What's it going to do with B?
Nothing.
It's been visited. C's been visited, D's been visited, E's been visited, F hasn't. So we'll call explore on F. And you can imagine what happens when we call F. F and G get visited and colored. And then it will consider G and not make the call because it's already been visited. So depth first search is a particular way of visiting all the vertices in a graph systematically. So just to animate it, It'll start with A. There's that first call to explore that we saw. Then it will call it for the second chunk. So how many times does DFS call explore? You've got an undirected graph.
V times. Or
No, it doesn't. It checks this. It makes this check V times. But on this graph, it calls explore twice. Now, if you ask how many times is explore called here and here, it'll be V times. But it's only called twice up there. What about for an arbitrary undirected graph? How many times is depth first search called? Yeah?
It's the number of like separated parts of your graph.
The number of clumps. Connected components is what we call them. So it's called once per connected component on an undirected graph. Now, suppose that here's an algorithm that uses depth first search. I want to associate a number with each vertex. And I want every vertex in the same clump, in the same connected component, to have the same number. So I'd like to number A, B, C, D, and E with 1, and F and G with 2. I want to identify the connected components of a graph. And all I have to do is make pre-visit do something interesting. So I'm going to have an integer called CC for connected component. It'll start out at 1. When we call pre-visit, it will set the CC number of a vertex. So imagine an array. It will set the CC number for that vertex to be whatever the current value of CC is. And here's the trick. After we finish exploring out of DFS, we increment CC. All right? So let's see how that works. We start visiting A, and when we color it yellow, we pre-visited it after that. So we mark it visited down in explore, and then we have to pre-visit it. So what's pre-visit going to do?
CC equals 1.
It's going to number A with a 1. Then we visit B, it gets a 1. C gets a 1. E gets a 1. D gets a 1. At that point, all the recursions return, and we're back up in that loop in DFS. So this call to explore finally returns because we visited the whole clump. Then we increment CC, and then we go find an unvisited vertex. So what will happen next?
Search everything until it finds out.
All right, it'll search and find F is unvisited, so it'll visit it and give it a number of 2. And G gets a 2. So that's an example of an algorithm you can build from DFS with a little bit of tweaking. Now, what would your graph look? Suppose you had a graph with no edges at all. What would this algorithm do? Yeah, it would number each one, it give each one a different number because each is its own connected component. Here's another one. Now this is going to look kind of weird at first, but this is actually far more important than the last one we looked at. This is a really crucial use of depth first search. In fact, this is why we're studying depth first search, is this algorithm right here. And here's the rule. We're going to have a clock that starts at 1. When we pre-visit a vertex, we're going to set, we'll call this its pre-number. Basically, we're going to record the time at which the vertex was first visited. So we're going to set its pre-number, its pre-value, to the value of the clock, and then we're going to increment clock. Similarly, when we're through exploring all the vertices out of a vertex, we're going to post-visit it and record the time at which it was post-visited. And this is something you need to get good at doing in your head. So let's watch how it works. We visit A, so we give it a pre-visit time. What is that pre-visit time? 1. Okay, what do we visit next? We visit B, and what's its pre-visit time? 2. We visit C, 3. What happens next? Not yet. We're done with C, and so before it returns to it from its call, what does it do? Right, it gives a post number to C. We're through with C at time 4. Now we're back up at B. It's going to explore out of that way. E's going to explore that. Well, E gets a pre-number of 5. Explores to D. What's D's pre-number?
6.
Okay, now we're through with D, right? No more. So he gets a 7. Now we're through with E, it gets an 8. B gets a 9. A gets a 10. Okay, now what happens?
Go to F.
This loop continues, it finds an unvisited vertex, namely F, visits it, and what's its pre-number?
11.
11. G gets to 12, post at 13, post at 14. So what this algorithm does is, for reasons I haven't explained yet, it records these pre and post times. What I haven't explained yet is why they're interesting, why they're useful. But the number of algorithms you look at are going to depend on these pre and post times. So you need to get to the point where you can look at a relatively small graph and just figure out what the pre and post times are. That's sort of simulating depth first search in your head. So with any questions I can help you with at this point? I would recommend taking these examples on these slides and trying to predict as you click through what the pre and post times are going to be, sort of like we just did. Okay, this slide does an analysis of the complexity of depth first search. But I'll just tell you, I'll tell you the answer. We're going to look at this analysis later. Not that, I don't mean to say that the analysis is unimportant. It's just I want to make sure I get to, there's a certain topic I want to get to today. So I'll do this next time. The complexity of depth first search on an adjacency matrix is O of V squared. The complexity of depth first search on an adjacency list is O of V plus E. So I put the question to you, could we do better? Could we come up with a depth first search? Is it possible there's a depth first search that will do better than V squared on a matrix? Or a depth first search that will do better than V plus E on a list? Or is this algorithm optimal in some sense? What do you think? Could someone smarter than all of us come up with a V log V depth first search algorithm on an adjacency matrix? Yeah.
I'm tempted to say no because it looks like with this order V squared and then order V plus E, it looks like those were the values for just the number of edges that we would have. But
I haven't explained the analysis, so just focus on the final answer. Yeah.
Do we use a breadth first search instead?
Well, okay, he suggested using a breadth first search, but the problem with the breadth first search is it doesn't produce these pre and post times which we need. And second of all, it's not any faster, but that's a different story. Yeah?
For a matrix, there's no way to go through and do better than like n squared because you have to visit all n squared locations.
So what he's arguing that for a matrix, you've got any algorithm at least has to look at every entry in the matrix, right? You can't ignore some edges. You've got to consume, you've got to read the whole matrix at some point over the course of the algorithm. That's going to take V squared time right there. If all depth first search did was just iterate through the matrix, V squared. You can't do better than that. That's the size of the data structure you're consuming. So, despite the fact of that V squared term, we call this algorithm linear in that the time it takes is proportional to the size of the data structure. It's not proportional to the number, it's not linear in the number of vertices, it's linear in the size of the data structure. Now what about this one here? List, O of V plus E. Could we do better than that?
The same principle, right?
Yeah, exactly the same principle, same argument. We've got to consume the entire data structure, and there are V things in the spine up there, V entries in the array, and there are E entries in the various lists. You've got to visit each one. So it's going to take, that's the size of the data structure, so that's the minimum time for the algorithm. So regardless of how you represent the graph, it's linear either way. Again, it's linear in the size of the data structure. So in that sense, that's the best we can do. Okay. take a break, and we're going to see some actual uses for these pre and post times. Okay, so let's consider depth first search on a directed graph. So it works just the same way, it's the same algorithm as for an undirected graph. But directed graphs, you're not going to be able to, for example, find the connected components with that algorithm we used before, because it's kind of hard to define what a connected component is. You know what I'm... So for example, do A and B belong in the same connected component? There's an edge from A to B, but there's no way to get from B back to A. So we're going to need a different definition for connected component, and we'll do that next time. Just the issues become more subtle when you've got directed edges. So let's do a depth first search on this one and get our pre and post times. So what's A's pre-time going to be? 1. And then what will it visit next? All right, so we'll go over to B, visit it. Now I've just colored that edge black because we are, it's the one, we actually followed it. We considered it and then we followed it. Now we visited B, and it gets a pre-time. What's that? 2. Which vertexes look at next? C. So consider C, it's unvisited, so it commits to it. C gets a pre-time of 3. There are no edges out of C. So a 4. Then we go back to B here. So I'm using the colors differently than any of the other animation. Right now, I'm using the color here to tell which vertex we're working on right now. So it considers going to E. Now, how can it tell E isn't visited? What property does E have that lets us know that E is not visited? Because I'm not coloring it yellow anymore.
Doesn't have a number.
It doesn't have a pre-time. So if there's not a pre-time, it's not been visited yet. So we really don't need the visited matrix anymore. So we'll commit to that. E gets a time of 5. We consider C, but bail out because it's been visited. I'll color that one orange. We consider D. That's good. Never been there before. It gets the 6. It considers the B. That turns orange because we've already been to B. So D gets the 7. What happens next? E gets the 8. We've exhausted all the ways out of B. It gets the 9. We get back to A. It tries to go to D. Fails. It gets a 10. So that was the first call to explore. What happens next? So we've got to pick up somewhere. So we'll just go in alphabetical order. It'll pick up at F. It gets 11. We visit G. It gets 12. We try to go to E. That doesn't work out. We get 13. We get 14. And that finishes the search. Now I've colored some edges black and I colored some edges orange. What was my strategy? What does a black edge mean? What was it over here? Yeah, it's one that I actually followed. And the orange edges are the ones that I didn't. If we ignore the orange edges, what do we have?
Spanning tree.
Someone said a spanning tree. We have, what we have is, you might call it a forest of trees. So we have a tree rooted at A that visits B, C, E, and D. No cycles, it's a tree. And we have a tree rooted at F. So we have 2 trees that cover all the vertices. So that's what you get when you do a depth first search on a directed graph. Now, is the fact that the edge from A to B is black, is that a property of the graph? Or is that a property of the algorithm? The algorithm. The algorithm could have decided to go to D first, in which case the edge from A to D would be black and the edge from A to B would be orange. So it's not like it's an intrinsic property of a graph. It's just what happens when the algorithm runs. So those black edges we're going to call tree edges. The orange edges, we have 3 names for them. The edges that go to an ancestor in the tree, we'll call a back edge. The orange edges that go to a descendant in the tree are called forward edges, and all others are cross edges. So what's an example of a back edge in this? An edge that goes from a descendant back to an ancestor. Yeah?
From D to B?
Right, D to B. So if you think of this as like, this is grandparent, parent, child, and then there's an edge back to grandparent. So it's going to an ancestor. That's called a back edge, going backwards in time, if you will. That's called a back edge. What would be an example of a forward edge? Okay, A to D is a forward edge. It goes from great-grandparent, the black edges go great-grandparent, grandparent, parent, child. And there's an edge going from great-grandparent to child, so it's going forward in time. What's an example of a cross edge, one that's neither a back edge or a forward edge? G to E, for example. Because G and E are connected by different black edges, so there's no relationship there. So there's one back edge, one forward edge, and 2 cross edges. EC is also a cross edge. Although they're in the same tree. What makes that a cross edge? It's between siblings, or between cousins, or second cousins, or whatever. But same level of the tree, if you want to think of it in those terms. All right, now, turns out you can identify, once you've done a depth first search, and got those pre and post times, you can identify what are the back edges, forward edges, and cross edges by looking at the pattern of the pre and post time. So let me explain what I mean. So let's suppose you've got an edge from U to V. And the post time of U is small, the pre time for U is smaller than the pre-time for V, which is of course smaller than the post-time for V, which is smaller than the post-time for U. In other words, the pre and post times of V are sandwiched by the pre and post times for U. So look at those orange edges up there and tell me which edges have that property. That the pre and post times of the from vertex sandwich the pre and post times of the to vertex. Okay, A to D is 1. See? A has a pre of 1 and a post of 10, which sandwiches the pre and post that are 6 and 7 for A and D. Do you see any others? What about D to B? Is that one? No, that's the opposite. The B is sandwiching the times for D. E to C is 1, I think, right? No.
Oh, no, sorry.
E is after C.
Never mind. They're just disjoint. And this one here is, all right, so we got the 1. So it turns out the only time you see that pattern is with a tree edge, but we already know what the tree edges are, or a forward edge. So you identify a forward edge just from that pattern. Yeah?
Is A and B an example?
Yeah. A and B. Yeah, A and B is an example, but that's also a tree edge. So tree edges and forward edges all have that property, but it's easy to know which are the tree edges, because those are the ones we followed. Okay, what the second pattern, which says the destination vertex times sandwich the source vertex times. Where do you see that happening? What was that?
D to B.
D to B, yes. B sandwiches D. And so that is characteristic of a back edge. And then cross edges have this property that they're just disjoint. The pre and post of V comes before the pre and post times for V. So those are the cross edges. So that's an example of information you can pull out of a depth first search. Now, one thing you might want to know is, given a directed graph, does it contain cycles? Now this one contains a cycle. Do you see the cycle? Yeah. B, E, and D. Can you think of a way, given what we just did, can you think of a way of using a depth first search to detect a cycle? Yeah.
It would just be anytime you have a back edge?
Right. Anytime you have a back edge. So if you detect a back edge, you have found a cycle. Now, as you're doing the depth first search, how can you detect a back edge? The situation would have to be, so think of that edge from D to B. For that to be a cycle, for that edge to be a back edge, B would have to have a pre-time, but not a post-time. So when we visit B, it'll get a pre-time. Then we visit D, it'll get a pre-time. Which will get a post-time first? D has to get a post-time first, and then B will. And so the times for D will be sandwiched by B. So if you are at a vertex and you discover an edge to another vertex that has a pre-time but not yet a post-time, you know right then it's a back edge. So if you're staying at a vertex like D and you see a vertex B that has a pre-time but not a post-time, you know that's a back edge and you know the graph has a cycle. So you don't even have to compute all the times. You can detect it as you're going. Yeah?
If you already had all the times computed though, like you already had the pre and post times, then would you then detect it by seeing like, you know, B's pre-time comes before D's pre-time,
Yeah.
B's post-time comes after that?
Yeah, you have to look at how they nest, like on the
Yeah,
last
like
slide.
All right.
Yeah. Yeah. So that's a way you can do cycle detection. And this just talks about what we just did, so I won't dwell on it. Okay. Now, an important subcase of directed graphs are directed acyclic graphs. So those are graphs without cycles. So that one I've changed the edge from D to E to point in the other direction. So now this one is a DAG. It has no cycles. So there's a DAG. And they're used for priorities. We saw some examples before. You could model prerequisite chains with a directed acyclic graph. Spreadsheets The cells in a spreadsheet form a directed acyclic graph because a cell can depend on other cells. But what happens in a spreadsheet if you try to have a cell depend on this cell and vice versa? So there's a cycle set. That's a problem. You got to fix it. And so there's a DAG there. Imagine something that models the operation of a vending machine. You know, what happens when you put money in and push the button? Sort of a flow chart without cycles. That's a directed acyclic graph. So a common thing you want to do with the directed acyclic graph is topological sort, which is to put the vertices in an order so that no vertex has an edge to a vertex that occurs earlier in the list. So if we were to linearize this graph, what vertex would have to come first? So we want the vertices, you know, all the edges have to go from vertices earlier in the list to vertices later in the list. A has to come first. What would have to come next? It has to be A and then D and then B. All right? What would be wrong with A, B, D?
D gets hit.
Yeah, B has to come before B because it has an edge from D to B. So in fact, there are three ways to linearize this graph. They all start with A, B, D, E. And then you got a choice. Once you've got A, B, D, E, C could come next or G could come next, because C and G are unrelated. And then you've got to make sure F comes sometime after G. It doesn't have to come immediately after G, it just has to come after G. Yeah?
So does topological sort require one of the edges to have no...
Okay? One of the vertices.
Vertices have no edges.
Right, so it's a property of a DAG that there's got to be at least, assuming there are any vertices at all, there has to be one vertex with no edge in. At least one. Why would that be?
Otherwise it's a loop.
Yeah?
So it has to be a loop.
Yeah, well, right, you have to start somewhere. If there were an edge into A here, then there'd be a cycle. There's no way to get an edge into every vertex without having a cycle somewhere. And similarly, there has to be a vertex with no edges out. In fact, here there's two. C and F have no edges out. So the ones that have no edges in are called sources. The ones that have no edges out are called sinks. So there's always at least one source and always at least one sink. That's what it says right there. So we need an algorithm to topologically sort a graph. And it turns out we can use that depth-first search algorithm to topologically sort a directed acyclic graph. And here's the property. In a DAG, every edge leads to a vertex with a lower post time. So how can we use that fact? That D will have a higher post time than E. E will have a higher post time than C. A will have a higher post time than both D and B. Yeah?
Just sort the vertices based on post time.
Right. Sort the vertices in descending order of post time, and you've got a topological sort. So this is the big payoff for these pre and post times, is to linearize DAGs. And the proof is simple. I'm not going to dwell on the proof. I just want to demonstrate what happens when we do the algorithm. The thing is, it does not matter how you make the arbitrary choices. So for example, to depth-first search this, if I were to do it the way I was doing it before and started with A as the first one, you'd all go, yeah, but yeah, sure, you chose A to come first, so it would have a high post time. So let me just show you that that's not the case. I'll start with G. It's a pre-time of 1, and then what's going to happen? F gets a 2, a 3, a 4. Now notice what happened. Everything downstream from G got a lower post time. Does that make sense that would happen? Right? You visit G first, now you're going to completely deal with everything that's reachable from that vertex. And they'll all get their post times, and then when the recursion finally returns to G, it gets the highest post time of the whole clump. So every vertex is guaranteed to have a higher post time. Well, now let's see what happens. What if we restart it here at E? It'll go to C, and we've got that property. E has a higher post time than everything downstream from it. But we didn't even go and visit this because it had already been visited. How did these end up with how do we end up with higher post times here? since this happened in a separate call to explore, how do we end up with a higher post time than there? Yeah, because if we had not visited before, we would have visited C, G, and F, and they'd all have lower post times. But since we did visit those before, they got lower post times that way, before we even considered D. So it works out either way. Now let's restart with D. So let's go visit B, and then we do A. It doesn't matter, if we sort by descending order of post time, we get A, D, B, E, C, G, F. Now what happens if we make the choices a different way? What if we do a mathematical order? What's going to happen? We get 1, 2, 3, 4. Okay. We come back to E and go to G, it gets a 6. That's just how it works out. A gets the highest post time of all, which it always will, no matter where you start the depth first search. There's no way you can make A not have the highest. And now when you do the sort, you get a different ordering, a different topological sort. Yeah?
So does this mean we can only detect sources, not necessarily sinks?
Okay, we detected a source because it has the highest post time.
Yes.
Well, what will be an algorithm for detecting sinks?
The numbers are right next to each other. And it doesn't.
Well, are the numbers, here's the problem, saying the numbers are next to each other. Suppose we visited C and G and F before looking at E. Then we restarted depth first search at A. E would end up with consecutive pre and post times. Because when we get to E, there's no way out, because we've already dealt with those. Yeah?
In this instance, the sinks have the lowest post order time. Is that always true?
No. And if that were even the case, how would you know? Well, if we just want to find one sink, let's see. Well, I guess you're right. In this case, it's true. I think some sink does have to have the lowest post time. I think you're right. I was thinking of a different algorithm, to reverse the graph, reverse all the edges, and do the thing again. And whatever is a sink in the reversed graph would be a source in the first graph would be a sink in the other. We'll play around with that some more. It'll become important next time. So what effect does making the arbitrary choices here have? It always gives you a topological sort, no matter how you choose which order to visit things. What observable effect does it have? Yeah?
The order of selecting which child to go to?
Well, that's the arbitrary choice. But how does that affect the output of the algorithm, which is a topological sort? Yeah, different arbitrary choices will produce different topological sorts. There are 3 possible ways, so we can find another way to do the depth first search that would produce the 3rd possible outcome. Okay, now, I'll come back to this complexity thing as well once we, I'll do this one, it's pretty simple. When we talk about the complexity of depth first search, we can talk about the complexity of topological sort. Here's another way to linearize. It's basically identify a source, remove it, repeat. So A is a source, so it's first. Now there's still one source, D, so it becomes next in the sort. That graph has one source, B. That graph has one source, E. Now you've got 2 choices, either C or G, they're both sources. Now you've got 2 choices, those are both sources. And finally one. So that's another way to do it, but it's simpler to use the pre and post times. Actually, post time is all that matters. All right, now, it's hot in the room, the lecture's been going on in a while, starting to drift off. I'm about to say the most important thing of the week. Algorithms on DAGs are most often organized in one of these ways. You topologically sort the DAG, and then you do a non-recursive, simple computation on each vertex in topological order. Or you do a topological sort and go in reverse order. Either way, if you're doing a DAG algorithm, the first step is topological sort. And then you either process the vertices in order or reverse order, depending on the demands of the algorithm. And these algorithms, the recursion in processing a DAG comes in the depth first search that does a topological sort. Once you've sorted it, you don't need to use recursion to do the operational, to do the computation of the DAG. You just do a simple non-recursive computation in order. So the topological sort is just done to get the order in which to do the algorithm. For some reason, students often ignore this advice, and they create massively complicated, inefficient algorithms on DAGs. And I often find it's the same students who won't use recursion or are uncomfortable using recursion when we're talking about divide and conquer, all of a sudden want to use recursion on DAGs. And you know, yeah, you use recursion, but that's in the depth first search. So this week's caddis problem, or next week's caddis problem, is a DAG algorithm. So just remember, the first step is going to be a topological sort. Okay? Let me show you some examples. We said we could do a spreadsheet, represent a spreadsheet as a DAG. So let's consider this. I have a spreadsheet with 6 cells, which I've labeled A, B, C, D, E, and F. What you see in the circle is the contents of the cell. So this cell contains a 5, that cell contains a 2. This cell adds, this cell multiplies, that cell adds. Which 2 cells does this thing add?
5 and 2.
Right, so this graph shows that, you know, dependency graph. So this is a spiral bag problem you saw in 3500. You know, plus this cell depends on that cell. Okay? So you think of the arrows as showing the direction in which information flows. This cell is going to take the value of A and E and add it, and similarly. And what I put outside the cell is the actual thing that's displayed in the spreadsheet. So this displays as 5, that displays as 2, this displays as 7 because 2 plus 5, and so on. So there's the setup. So you've got that DAG. Suppose vertex A changes from 2 to 7. We've got to update the display. We've got 6 cells. So how do we do that? Do we start by going and recomputing the value of C? And then doing F and B and work backwards? No. Because the one that changes is A up there. The answer is we're going to do a topological sort. And we're only going to sort the ones that are reachable from A. So we don't even care about E won't be involved. So we start at A, we do an explore from A, we get the post times, and we do a sort. And one possible outcome of the sort is going to be A, D, B, F, C. In fact, that's the only topological sort that can happen for that subgraph. So we don't even do a full depth first search. We just explore starting at A, and we get A, D, F, B, C. And then we evaluate in that order. So what happens when we change A to 7? We evaluate it. It says evaluate A first, so its value changes to 7. Now it says to evaluate D. Okay? So 7 plus 5 is 12. Now it says to evaluate F. I guess I did have my choice. B or F could come in either order in the topological sort. So let's say I multiply 7 and 12. I get 84. Then I compute F. I'm sorry, then I compute C.
What happened to computing F? There should be 144.
Yeah, well, I messed up. What did I forget to do? I forgot to recompute that.
That should be 60.
A, D, B, F, C.
Yeah.
Or, yeah.
Yeah, A, D, F, B, C works. I just forgot to do that. Yeah, it's supposed to be 60. I don't know. Anyway, sorry about that. Hopefully you get the main point. Why did this work out? Why does it work to do it in topological order, topological sort order? Yeah?
Because by the time you get to each vertex, you've already guaranteed that the previous ones have been updated already?
Right. The topological order guarantees that when it comes time to evaluate, say, F, you're guaranteed to have reevaluated everything that it depends on that could have possibly changed. Okay? So that's the topological sort. Now, what's the simple computation you're doing at each vertex? Yeah? Oh, that was a stretch. I always say it's a simple computation. What is the computation you're doing?
Log of V.
No, what's, I mean, just in words, what do you have to do to evaluate this vertex to find out it is 60? You have to find all the edges into U, go back to those cells, get their values, and multiply them. No recursion required. Now, if you start over here, you have to say something like, okay, recursively search back and evaluate everything you reach, and then when you're done, do that. And you can end up with exponential running times that way. Just do a topological sort, do it in order. Yeah?
So topological sort sorts all the vertices in a graph. But in this case, we ignored E.
Right, so topological sort, if we just care, in this case I just cared about starting at A. And I did a topological sort. Instead of using breadth first search to do the sort, I did explore starting at A. And that just sorts the things that are reachable from A. So it does two things. It figures out the right order. It also figures out which cells don't matter. Because there could be thousands of cells. And we just care about this little chunk of the graph that really do matter. Yeah?
If you were to update, like B, for example, would you start at B then?
Yeah. So let's suppose you decided to update B and change it to something. Say you change it to minus. You do a topological sort starting at B with an explore instead of breadth first search, and you just get B and C. As this, and you just reevaluate B and C in that order. Okay? Now, maybe some of you are thinking right now, well, I did a 3500 spreadsheet project. I don't remember doing a topological sort. So what gives?
Sanity?
No?
We got handed this big.
You got handed a method in the spreadsheet class that did a topological sort. There was an important method, and I just know from experience with 3500, there are people that ignore the method. So it seems that this unwillingness to topological sort extends even to there. But essentially, it was done for you. Okay, what about this problem? I want to know the number of different paths there are leading from a source to a vertex. So I've solved the problem up here. There's one way to get to A. We'll just say there's one way to get to a source. How many paths are there to get to B? How many ways are there to get to B? One. You go from A to B. How many ways are there to get to B? Two. A to B, or A to B to B, and so on. There's 6 ways to get to F. So, this paths of F up here, this the value, that's what's in white up there. How do you compute it? What's this? Yes?
If you're looking at a certain vertex, you can just, it looks like you can just add the...
Okay, notice the property. This vertex is labeled with 1. It has the sum of all the vertices that come before it in the graph, that have an edge to it. So B contains a 1 because there's one edge in and there's a 1. B contains a 2 because there's an edge from A, it has a 1, there's an edge from D, there's a 1. Okay? So how do you calculate them in the first place, though? Yeah?
Start with your source.
Right. What you do is you start with a source and work forward. You don't want to be calculating the number of paths to G until you've calculated the number of paths to C and the number of paths to E, and so on. So it's a DAG problem, so the first thing you think about is topological sort. All right, so let's see how that works. There's a topological sort, and this just says that if a vertex is a source, its value is 1. Otherwise, we add up all the values. That just says add up all the values of the edges leading in. Okay? So we're going to label A with a 1. What are we going to do about D? We're going to add up the paths value from all the vertices that are on the other side of the edge that leads in. So that gets a 1. Now it says to do B, so it gets a 2. 1 plus 1 is 2. What's E going to get? 3. C is going to get a 3. G is going to get 6. F is going to get 6. Again, the computation at each vertex is simple. There's no recursion. You just say, okay, what leads to me? These two edges, you just go see that's a 2, that's a 1, add them. if you do the topological sort, it pays off in a simple computation. One question to end on. How do you go back from E to D? The data structure is designed to, if you want to know there's an edge, a directed edge from D to E, you can find it. It's not stored the other direction. So how can you efficiently find the edges that lead into a vertex in an adjacency list? Yeah?
The different topological permutations?
No, the topological sort works the same. Yeah?
Just reverse the graph first.
You need to, what you'll need to do, if you need to access predecessors in a directed graph, you need to take the time to reverse the graph. That's a linear time operation. You basically just create a new graph where all the edges are reversed. And now you can go either way in the graph. And you use one direction to sort, and use the other direction to find the predecessors. So you can add them up. Okay? So my goal today was to get to this point so that you have a fighting chance to work on the caddis problem if you want to. We'll talk more about this next time.